Okay, so here's the same formula in the text. And now let's try and do an example. So here we're going to take a vector A and a vector B, and we're going to ask what's the angle between them. Now, if these were just vectors in R2, we could probably figure out some way to get the angle without too much difficulty. But these are not in R2. You can see there's an I, J, and a K here, so we must be talking about 3 dimensions. So it's not so straightforward to get the angle between such vectors. But here we can use our formula, and it's not going to be very hard. So what do we have to do? We just have to take the dot product of these two, which we know how to do that. We just have to remember that here there's no kth component, and here there's no ith component. So actually, those components are kind of going to disappear, and all we're going to be left with is the jth component is common for both of them. Both of these have a coefficient of 1. This one has a coefficient of 1, and this has a coefficient of 1. So this is going to be 1 times 1, which is 1. Well, you can just check this out for yourself. And then on the bottom, we need this stuff. So we need the norm of A, which means the length of A, but it also means A dot itself and the square root. And you can figure out what A dot itself is for this one and take the square root. And you can figure out what A dot itself is for this one and take the square root. And it turns out that each of them is the square root of 2. So we end up with the square root of 2 over the square root of 2, which is obviously 1/2. And so theta is the cosine, the inverse cosine of 1 over 2. Theta is the inverse cosine of 1 over 2 here. So remember, the inverse cosine means we want to take the cosine of something and get 1/2. So what is it that we have to, what angle is it that we have to take the cosine of to get 1/2? And it's pi over 3, which is 180 over 3, or 60 degrees. Anyway, you can probably figure this out, or you can try to remember this. But anyway, it turns out that the angle is pi over 3. So we were able in 3 dimensions to figure out what the angle was between two vectors by using this formula. And that's good, and we might be able to get that on our own without using this formula, but we definitely can't get it on our own if we're talking about 5-dimensional objects, not just 3-dimensional objects, because there's no such thing as the angle between 5-dimensional objects. But here, we kind of give a meaning, even in the case of 5-dimensional or 6-dimensional, whatever dimensional objects we want, we can kind of give a meaning by using this formula. So that's what's interesting about this formula. Okay, so suppose we have two vectors A and B, and when we do the dot product, and I'm not talking about where we know the magnitudes, we have, for example, the coordinates of A and the coordinates of B, and we do the dot product, and we find that the dot product is 0. So what can we conclude? Well, presuming that neither of these, neither A nor B was the 0 vector, 0, 0, 0, or all the entries are 0, then it can't be true that the magnitude of A or the magnitude of B was 0. So according to this formula, the only thing left is that the cosine of theta is 0. And what does that mean? That means that the two vectors must be perpendicular. Another word for perpendicular in terms of vectors is orthogonal. And this word is used more often when we're talking about n-dimensional vectors, or more than 3-dimensional vectors. So perpendicular makes sense in 3 dimensions, but we usually shift to the word orthogonal when the dot product is 0, but neither of the vectors are 0. One more thing, they usually say that since the 0 vector, if you dot it with any other vector, will give you 0. It sounds strange, but just to be sort of consistent, we say that the 0 vector is perpendicular to every vector. So as an example, I plus j, which I think we saw before, and this one, no, we didn't see this example before, but if we take the vector I plus j, so notice it doesn't have any k component, so it's only in the xy plane, and then this vector, and we do the dot product, and we get that the dot product gives us 0 if we check it out. Then what do we say about these two vectors? We say they're orthogonal or perpendicular. Okay, so the last topic that we want to discuss is what's called vector projections. So let's take a look at this picture here. And here we can see that we have a vector A and a vector B. So the idea of a vector projection, and we're talking about projecting B onto A, is basically like the shadow of B. So you imagine that there's a light up here and it's shining down, and the shadow will be here. In other words, this part will be dark and this part will be light. So the shadow that's cast by B onto A is called the projection of B onto A. So we can see that the projection of B onto A goes from here to here. It's in the same direction as A. In this case, it's longer than A, although it could also be shorter than A. For example, if B only went up to, say, about here, then the projection would be down to here, and the shadow would be here. So the projection, the best way to think about the projection is it's just the shadow. But the notation is a little bit annoying or a little bit confusing, and because which is the base, and A is the base. So where do they put it? They put it down here. I'm not sure exactly if that's the most intuitive place, or maybe it is. I'm not really sure. But anyway, we just have to get used to that. So the base down here is put here, and we're talking about the projection of B onto this thing. So that's the notation. Whether we like it or not, we have to get used to it. Now we can also do it in this case as well. You might say, well, what's the projection? A is over here, but we imagine that A sort of extends everywhere along this this line. And so the projection now is the shadow, which is actually in this direction. We also say that it's a vector. The projection of B onto A is a vector. So it's not just this base here, but it's the vector that goes from here to here. So it has a direction as well. It's not just the length. And same thing here. It's not just the length from here to here, but it's the vector from here to here. So it has this direction. So this concept has applications in physics when you're talking about forces and objects moving and so on, but we won't worry about that. We just want to understand the mathematical definition, which is, as we said, it's a vector and it's basically the shadow. Okay, but we want to get a formula for this thing, the projection of B onto A, the projection of B onto A. Now, clearly it depends on theta, right? If theta is smaller, then we're talking about an angle like this, and so the projection of B onto A will be longer or have more magnitude. But one thing to remember is it has to be in the direction of A, either the same direction as A or 180 degrees. Okay, now to get a little more insight into this, let's draw a unit circle with this as the center. Okay, so let's suppose that this is a unit circle. In other words, its radius is 1. So if this is a radius, then the length is 1. Okay, and let's assume that the angle theta is less than or equal to 90 degrees. If it's greater than it, we'll have a slightly different analysis, but let's assume that it's less than or equal to 90 degrees. Okay, so I can't type in theta, so I'll just spell it out. So the cosine of theta would be the length of this red line here. But of course, we really know that it's the length of the red line divided by the length of the radius here, which is the hypotenuse of this triangle. So if we want to know the length out to here, what is it going to be? It's going to be, I'm sorry, if we want to know the cosine of theta, we can, instead of using a unit circle, and then we have to divide by 1 here, we can use the full length of b, so we're going to divide by b, and then we're going to get this length here is going to be the projection of b onto a. So what we get is that the cosine of theta is the projection down here divided by b. Now we should put the length actually here. So let me put the length in there. So now this makes sense, right? The cosine of theta is the projection of b onto a, which is this length here, divided by this. Actually, I think I need that if I don't want to restrict theta to be less than or equal to 90 degrees. Now, if we want to generalize this, we should have the double bars around, I'm sorry, not around this, but around this and this, because if we want to allow the vectors not just to be in 2 dimensions, but 3 dimensions or more, we should use, or 4 dimensions or 5, we should use the double bars, the norm, in other words. So this is what we get. So we can make this statement here, and it's based on trigonometry, as we just saw. So then we can write this, we just bring this over to this side, and then we can just put this on top and this on bottom. That doesn't do anything. So we get this divided by this. We started with this, and then we just multiplied the top by norm of a, and then divide by the norm of a, so that doesn't do anything. But we get this expression. But then we can recognize the top as the absolute value of a dot b. And remember, we're working on getting a formula for the projection of b onto a. Okay, so now we have a pretty nice formula for not quite the projection of b onto a, because we have the norm around this, but still it's a pretty good formula. Now, to get down to the actual formula for the projection of b onto a, not the norm of the projection of b onto a, we need this proposition here, which we'll look at in a minute. But let's just look at what the formula looks like. So it's pretty close to this, but it's not exactly this. We want the projection of b onto a, not the norm of the projection of b onto a. So let's look at it. So this is the absolute value of a dot b. And why is this only the absolute value? Why don't we need the norm around this? Because a dot b, remember, is a number, or as we say, it's a scalar. It's not a vector. We made that clear earlier. It's not a vector, so it's just a number, so we can use the absolute value for that. But a, we can't talk about the absolute value of a, but we can talk about the norm, or the magnitude of a. So anyway, that's what we have here. So let's see what the actual projection of b onto a is. Let's skip down, and the projection of b onto a is a dot b over a dot a times a. Now, just one careful thing about this, and that is, what is the stuff in the parentheses? I mean, is it a vector or is it a number? Let's just check that first. So a dot b, is that a vector or a number? It's a number. A dot b is a number. We made that clear before. And what about a dot a? Is that a vector or a number? That's also a number. So we have the top is a number and the bottom is a number. So a number over a number is, of course, a number. And so what are we getting here? We're getting a number times a. Well, that's good, because we want it to be in the direction of a, and it will be in the direction of a, because this is just a scalar times a that's just stretching out. A, or maybe flipping it over in the opposite direction, but basically it's in the direction of A, and that's exactly what we hope, because going back to the picture, it's supposed to be in the direction of A. Okay. Anyway, we had this formula so far, but we want to get down to this formula. So we need to do a little bit more work, and then we'll be done with this chapter. So they have this proposition here. They say let k be any scalar and a any vector, then the magnitude of k times a is equal to the absolute value of k times the magnitude of a. Well, this looks kind of reasonable, but it has to be proven. And then one more, and this is important, a unit vector. So a unit vector means a vector with length 1. So vectors, of course, they can be in all different angles, and they can be, of course, in many different lengths. But a vector which is length 1 is called a unit vector. It can be in many different angles, but it has to be of length 1. So a unit vector, okay, that means a vector of length 1, in the direction of a non-zero vector A. So we just want to talk about a vector in the direction of A, but only of length 1, or only a unit vector. So here, let's go back to the picture. So here is a vector A, but this vector may be longer than 1, it may be shorter than 1, we don't know, because there are no numbers written here. But it could be of all different kinds of lengths. But if we want a unit, we can talk about a unit vector in the direction of A. That means it's pointing in the same direction as A, but it's only of length A. Sorry, it's only of length 1. So this is a very nice formula. It says that a unit vector in the direction of a non-zero vector A is given by A divided by something. Now, in order for this to make sense, the something better not be a vector, because we don't have any concept of a vector divided by a vector. We have no such definition. So this better not be a vector down here, and of course it's not. This is the norm of A, which is a scalar, it's just a number. So that's fine. We can divide a vector by a number. We're just scaling the vector. We're just stretching it out or shrinking it, but that's fine. We can do that. So anyway, this is the formula for getting a vector in the direction of A that has unit length. Okay, these are not, this is not so hard to prove, but we want to prove it. Okay, so they say part 1 here is left as an exercise, so you can try and prove that yourself. They give us some idea about how to do it. Okay, for part 2, but basically what we want to show is 2 things. We want to show that this thing is of unit length. It means it has its length 1, and that it's in the direction of A. Well, the second part is not too hard, that it's in the direction of A. We know that. If we're just taking a scalar times A, it's always in the direction of A, especially if the scalar is positive. I guess if the scalar was negative, then it would be in the opposite direction of A, but this is going to be a positive number, the norm. So it's pretty clear that it's in the direction of A, but it's not necessarily clear that its length is 1. The length of this whole thing is 1. So that we need to show. So for part 2, we must check that the length of this thing is 1. So what does that mean? Well, we want to take this thing and calculate its norm, because that's what we mean by the length. We want the norm of this thing inside. But we can take that and write it like this, of course. And then we're allowed to bring this part out. And why is that? Because presumably we just proved this part 1, which says exactly that we can take a constant outside of the double bars. So that's what we're doing here. We're taking this, which is a constant, taking it outside of the double bars. So And the double bars are only now around A. But then we clearly get the top and the bottom are the same, so we clearly get 1. And so we've proved that this has unit length. Okay, so we proved this proposition 3.4, and now we want to go back and show that the projection of B onto A, not the norm of it, but just the projection of B onto A, we want to show this. And we've already shown this part here. This is equal to this. So what does it say? This says that the length of the projection of B onto A is this. That's what that means. It means the length of what's inside is equal to that. So here they just repeat that. The projection of B onto A is a vector of length like that. That's what we just said. And it's in the A direction, or the plus or minus of the A direction. So if it's in the A direction, remember, what is this? This is the unit vector in the direction of A. So of course this is in the direction of A, and we're just scaling it by this to make it long enough, because this is the length of it, and this is the unit vector. So when we multiply the unit vector by the proper scaling, we get the projection of B onto A. Now the top part we know we can write as this times that. We've discussed that before. And the bottom part is this, and then we have times this. So hopefully that's clear. And then I'm going to let you read this stuff in this paragraph here. And having read this stuff, they make it clear that we don't need the plus or minus here. And we can take away the absolute value sign around the cosine of theta. I'll let you sort of figure that out. And now we can collapse this part to A dot B, and then we have A, and then we have this squared, which is here. And so finally, we get that the projection of B onto A is here. And that's because this A dot A is equal to the norm squared, and we discussed that before. And so we have finally this formula for the projection of B onto A. And as I said, the stuff in here is just a scalar. So this is a scalar times A, and so we're still in the direction of A, but we've moved out by a certain amount. And so that gives us the proper formula for the projection of B, which is the vector up here, onto A. It has to be in the direction of A, and the formula we've gotten is in the direction of A, but it's scaled by this. So they say that this is not difficult to remember. Well, I'm not sure about that, but maybe you'll remember it. Anyway, the concept is important. The projection of one vector onto another, and the formula, after we've proved it, looks like this. So again, this is in the direction of A multiplied by this scalar. Okay, that's all we're going to do. So we'll stop.